So our next presenter is Petra Gutenbrunner, and she worked 6 years as software developer and studied afterwards in biomedical informatics at University of Applied Sciences, Upper Austria. She received her bachelor's degree in 2014 and her master's in 2016. And during her studies, she did 2 internships at Wellcome Trust Sanger Institute in Cambridge, UK, where she worked on computational proteomics pipeline for protein identification. After her master's, she joined Jürgen Group, and her research focus is development of computational approach for ancient protein identification within Mascot. I would like to welcome now Petra.
So welcome to everyone also from my side. And so we heard a lot of the amazing techniques behind the mass spec, and now we are looking into how to identify the experimental spectrum resulting from this mass spec analysis. And a common way to do this are database search engines, and here I'm talking about Andromeda. So it's called Andromeda 1.0 because this is the conventional Andromeda score calculation, and tomorrow we will hear the extension of Andromeda 2.0. So first, I want to give you a brief introduction on a typical shotgun proteomics workflow. So probably you all are already familiar with that, but I just repeat it quickly. So everything starts with a protein mixture, and you digest those using proteolytic enzymes into a complex mixture of peptides. And if you do, for instance, phospho analysis, you're specifically interested in phosphorylated peptides, like indicated here with the star, and you're able to enrich for them because they're low abundant. And yeah, so you can apply different enrichment techniques on that. And then when you have your complex peptide mixture, you subject this to HPLC to sort them, and then they are further ionized and then subjected to mass spectrometry. And here to tandem mass spectrometry, which has the additional step of fragmenting a peptide based on the precursor ion to MSMS spectra. So then you have the resulting experimental MSMS spectra, and then we want to identify those. And here this is done via database search. And quickly how it works. So you have the experimental spectra, and then you generate automatically theoretical spectra based on the protein database, and then you match those theoretical spectra against the experimental spectra. And this matching is called peptide spectrum matching, short PSM. And usually for one experimental spectrum, you have more theoretical spectra that could possibly explain the experimental spectra. And therefore, to tell which one is the better one, you have to validate them based on the scoring, so the Andromeda scoring. And then the PSM with the highest score explains the experimental spectrum. So now let's move on into the scoring. So for this, processing of 2 major branches is necessary, and the first one is processing of the raw file, which contains the experimental spectra, and then when we have done this, we generate the theoretical spectra, and then we match those. And now I go into detail into those steps. So first, the processing of the experimental MSMS spectra. They're usually available in a binary file format, raw files from Thermo. And yeah, we have to do here some steps, but before that, I want to also show you where to select these raw files when you want to do a search in Mascot. So you open Mascot, and then you see at first the tab raw data, and here you can press then the button load, select your raw file which you want to analyze, and yes. So as I said, or I don't know if I said it, but I repeat it. So these raw files are very complex and large, and to allow fast processing, you have to reduce the complexity. And this is done now in the next steps, which I'm going to explain. So first, to reduce complexity, centroiding can be done. So often the spectra come in profile mode, And for further processing, we don't need the 3D information, so we can reduce this, and then so we do centroiding. And sometimes the raw files are already in centroid mode, and so in that case, nothing needs to be done. Then to even more reduce the size, we can do de-isotoping, but here it's important that the spectra is in high resolution. Otherwise, it's not possible to detect the isotopic pattern, since you can't really tell if two neighboring ions are 1 Dalton apart in case of charge 1, or if they belong to different fragments. But if you have high resolution in case of Orbitrap or Q-exactive, you are able to detect the isotopic pattern. And to reduce the complexity, the isotopic pattern here is taken out, and then we reintroduce the monoisotopic peak when summing the intensities up. And also, as already explained by Jürgen, when you know the de-isotopic pattern, since the distance between the ions is divided by the charge, you know that also the charge based on the isotopic pattern, and then so you are also able to transfer higher charges to charge 1. So, and if we have two de-isotopic pattern for the same fragment and different charge states, so we introduce the monoisotopic peak, we transfer it to charge 1, and then we sum those up. So with this also helps then for the matching when the spectrum is not as complex anymore. So now we reduce the complexity already, but we can do another step, which is the filtering that can be done. So here the filtering is called the top Q filtering, and this is also a noise reduction, because how it's done, so you filter the top Q most intense peaks per 100 Dalton window, and also why it's called Q, because this is a parameter that is defined in max quant. So in theory, you would be able to change this, but 99.9% I would say you don't need to, only in really specific cases. So this value is by default set to 12, and then you take different values out. So first you take the 12 most intense peaks per 100 Dalton window, do a scoring and see how many peaks are matching. And then you go on, offer just 11, 10, and see how many are matching, and then you go down to 4. And so while doing so, you also introduce intensity dependence, because the higher intense the peaks are, the more likely they are matching. And if you are offering more, then of course more are matching, but also it's more likely that they are matching. And when you offer just, for instance, 4 intense peaks and 3 of them are matching, this is really good, and it takes also then the score this into consideration, but more about that later. So here we filter those, and at this step we're done with the first branch, so we have processed our experimental spectrum, and now we can move on to the second branch, where we generate the theoretical spectra. And so I will explain you this now in detail. So as I mentioned, the theoretical spectra are generated based on a protein database. And the protein database you select based on the, so you take the peptides which you would expect in the sample which you want to analyze. And so here I also want to show you where you can define these FASTA files in the max quant search. So when you open it, then you have the third tab, global parameters, subsection sequences, and here you can add then the FASTA file. Yes, so now this is an example how such a FASTA file looks, and also so you have here several protein sequences, and when you know in the sample preparation step you have the proteins and then you digest them into peptides. So when we generate the theoretical spectra, we have to do the same computationally. And therefore, we also take those protein sequences, and from the sample preparation, we know also they are used enzymes, so we know at after which amino acids the cleavage should happen. So here, in case of trypsin, we know exactly that we have to cut this protein here on these positions, and then we get the list of peptides. So as next, we have other information what we have to configure in the search, which is the fragmentation method and the variable modifications which we expect. So based on this information, we can then go and have, okay, we know now the peptide sequences, and for each of the peptide sequences, we have to calculate now theoretical spectra. And so here the fragmentation method is important because based on that, you get a different ion series. So here is an example, HCD, you end up having the ion series B and Y. And so based on that, you know, you need to calculate these masses for those ions. And then in case you have modifications, like here, this peptide is here phosphorylated. You see here the shift based on the mass of the modification. So when you have one peptide sequence and you think there are more modifications, so you define them in your search because you expect these modifications on the peptides, then you have to generate for all of these peptides also all combination of all these modifications in order to be able to identify those. So that's why you should be careful when you define the modifications as search parameters that you don't like, okay, I think I just set 20 because I think they're all in there, but this is negative because you increase the search space. And then also you add, you offer theoretical spectra which are not really necessary, and you make it much more complicated because you also identify false positives. They are still regulated by the FDR, but yeah, just select the modifications which you really think they are in there and they're really helpful. So as next, yes, here I want to also show you where to set the modifications in your search. So you go to the second tab, group-specific parameters, modifications, and there you can select variable and fixed modification. So fixed modifications are the ones that are always occurring on the peptide, and variable, they are the ones they can or not. Yes, I forgot to show you where to set the enzyme. So this will happen here in the digestion step. Then I mentioned the fragmentation method is also important, and here I quickly explain you the most common ones. So here we have CID and HCD. They are pretty similar. So they offer the same ion series, which is B and Y, but the resolution is different. So HCD offers a higher resolution. And so how does it work? So you have the peptide sequence, and also you bombard it with inert gas, and then based on the kinetical energy that is transferred to the peptide fragments. And this is usually happening on the peptide bond. Yes, and then we have ETD, which works differently. So you transfer the electron of a radical ion to those peptide, and then this causes an imbalance in charges, and this causes the peptide to break. And this results in a more complex pattern. So here this is C and Z, and it's between the nitrogen and the C alpha bond. And then also a quite new method is UVPD, and here you use ultraviolet light to fragment the peptide, and here we have all kind of fragmentation patterns like A and X and B and Y and C and Z. So now, yes, so maybe an additional information here. So just to clarify this a bit more. So why is this important? Because you can see here clearly like CID fragments here. So you would not include these elements for the calculation of the fragmentation. And here, when it's the ETD here, you include that into calculation. So these are the differences which are important when you calculated the masses for these fragments. So to offer all these ions in the theoretical spectrum, we do different combinations here. So for CID and HCD, as I mentioned, this is our B and Y ions. And then at the beginning, I told you that sometimes in order to detect the isotopic pattern and to convert higher charges to charge 1, the resolution is important. But if you're working with a file that is not high resolution, then you can't transfer higher charges to 1, so you also have to offer the higher charges in the theoretical spectrum. And that's why we do this here, but this is depending on the charge of the precursor, so this should be at least above 1. And then also, if the peptide contains amino acids, some of them are prone to losses, like water losses and ammonia losses. So here we also include them in the theoretical spectra. And then some modifications, especially phosphorylation, they also have some neutral losses. And also in case of the phosphorylation of tyrosine, there are diagnostic peaks that are also taken into account. So for ETD, as we already figured out, it looks a little bit different. So as I said, the break happens between the nitrogen and the C alpha. And then also through the hydrogen radical transfer, so we can have here also a combination of C minus 1 and Z prime, which is Z plus 1. And then also it can happen that we have a combination of C plus 1. And so we're taking all these combinations into account. So we offer always like C, Z, and C prime ions in the theoretical spectra, but then we try different combination. Once we also add, in addition to this, the C minus 1, the C plus 1, do a scoring C, and then compare the scoring to this version, and then we add once the Y, and then we combine all, and then so we do some score optimization based on different combinations. Yeah, so we're done now with the second branch, and I think we are ready now to match those two spectra against each other, and let's now look how this works. So here we have the experimental spectra, here the theoretical spectra, and now we want to match them. And here we also define a tolerance for matching those peaks of this spectra. So when we have high resolution, we have ppm-based tolerance, and when it's low resolution, it's usually Dalton. But the good thing about MaxQuant is here that this is automatically set. Because it reads the information of the resolution out of the raw files, and then it gives you a suggestion, and so you don't need to worry about this, and this is really nice. And then you can see how many peaks are matching between those spectra, so you count that, and then you have the variable k, the number of matching ions in the spectrum, and then you have n, the total number of ions in the theoretical spectra which you offer. And then you feed these values into the binomial probability-based scoring, and then you calculate the probability of getting at least k matches by chance. Then you multiply this value with minus 10, the decadic logarithm, and then you get your final Andromeda score. So as we know already, there is optimization happening. I repeat it here again. So we have the top Q parameter, so where we take, as you can remember, per 100 Dalton window once 12, then 11, and go down to 4, and then we calculate the score. And then here also neutral losses, because some amino acids are more prone for that, and also modifications. And then with the ion series, as we have seen for ETD, we offer different combinations of ion types, and then so we do everywhere scoring, and then we take the best to consider all possibilities. Then now let's have a look how it is with modifications. So on this is an example based on the phosphorylation and it can get quite complex, because for instance here we have the peptide sequence. We know there are 2 phosphorylations on the peptide, but since phosphorylation can happen on serine, threonine, or tyrosine, we would have 4 different possibilities. And so we have to try all those combinations, so we result in 6 combinations. And then if the peptide is also very long And if you have more phosphorylation or the combination with other modifications as well, you have in the end a really long list of combinations. And so we split this problem up into two. So first, we limit the number of combinations to 200 to figure out, okay, what are the most likely modifications happening on the peptide. And then when we know the modifications, and there are also phosphorylations or other ones which have more possibilities, side possibilities, we look then into detail and offer a combination for 100,000 combination to figure exactly out on which side the phosphorylation, for instance, is happening. Then Jürgen, in his talk, already also mentioned the problem of co-fragmented peptides. So here, this will also be identified. So just a brief explanation how it works. So when the precursor is selected for MS2 fragmentation, there is an isolation window placed around the highest peak of the isotopic pattern. And this is symmetric because you can expect the isotopic pattern on this side or on that side. But when you do this, it's also possible, so you would expect the blue one, but you also co-fragment the green peptide, but also a little bit of the yellow. And you would like to identify those peptides. And quickly explaining how it works. So because with all this mass recalibration and everything, we have a very exact tolerance that we can apply. So we really can limit the possible peptides that could identify those spectra. And so we first try to identify the blue peptide, and then when we know the peaks that are matching to the blue peptide, we take them out. And then we try to identify the green peptide. And also here at the beginning, we do also the top Q intense filtering on this new again. So this is done for each separate peptide identification again. And so when we identify the green one, we take again the ions out, and then we try to identify the orange one. Good, and then let's talk now about the posterior error probability. So to give you an example, or to try to explain you better how it works is, so for instance, you get a big parcel delivered from Thermo, and you know it's 412 kilogram heavy. You can either think it's a microelephant, or you think it's a Q exactive from Thermo. So when you look at this example, you see, okay, with the information that this parcel was delivered by Thermo, you would already know that, I mean, it can't be the elephant. So you have already an idea of what is more likely to be the correct identification. And so depending on the properties, you know which one is more likely the correct one. So now let's try to transfer this idea also to peptide identification. So here we have an example that we have an experimental spectrum that has two possible explanations of peptides, and we know it's triptych. And here we have a nice peptide identification without modification, no miscleavages. On the right side, we see a peptide identification which has oxidation, 2 times phosphorylated, and 2 miscleavages. And so you also would assume, okay, the simpler identification or peptide is more likely to be the correct one. And to calculate this probability, which one is more likely the correct or wrong one, we calculate the posterior error probability. And yeah, depending on the properties, the PEP can be different. So peptide properties are, for instance, the score, the peptide length, the number of modifications, miscleavages, and charges. And based on these properties, you group or classify those peptides into classes, and then you calculate for each of these classes the FDR. So when you want to know 1% FDR, it can happen that the PEP, which you calculate, are for this class is different, and so you cut it off at 1% FDR, and so you have a different resulting PEP for each of the classes, and then between the classes you need to adjust them that they're equal. Yeah, so there are different approaches like Percolator, which is a machine learning approach, but basically it does the same. So it also classifies them, and then it calculates FDRs for different classes and brings them together. Yes, now I want to mention the protein FDR. So it's also very important to set that in order to control not only the correct identification of PSMs, but also the correct identification of proteins. So otherwise, it can happen that when you analyze a sample, which definitely does not contain this kind of proteins, in that case, olfactory receptors, but you would still be able to identify those. And if you apply protein FDR, you can filter those out. So it's very important to also consider this. And the protein FDR is calculated based on the PEPs of the PSMs that identify these proteins. And then, yeah, when you apply the PSM FDR, you have a number of resulting PSMs left that make it through the FDR control. And then when you apply on top of that the protein FDR, then it can happen that some proteins are filtered out, but also then the PSMs that are grouped to that or aligned to that, but they made it through the 1% PSM FDR. So it can happen that in the end, applying also on top the protein FDR, you get not as many PSMs anymore as you would only apply the PSM FDR. And then there is another column in the output file of the protein groups. So here you have, when you are interested in phosphorylation, for instance, we also offer only identified by sites. So maybe there is a phosphorylation on the protein, but this would not make it through the FDR. But we still want to offer you this information of the phosphorylated proteins. That's why we leave them in, and you should kind of filter them out. And then when you do comparison between search engines, make sure that you really apply the same settings on both sides. So, yeah. And as next, is there still time? So here is just a comparison what was done. So we compared the Andromeda score against the Mascot score, which is also based on a binomial probability. And we can see here that the score distribution is equal. There are no major outliers on the axis. So there are no additional identifications on one of the sides. Then when we look at the PSM false discovery against the coverage, we can also see that they're performing quite similar. And we did the same on phosphopeptides, and here it behaves also similar, and also no major outliers on the axis. And then on here the same. So they have a similar precision and recall curves, and maybe at the very high specific region here, the coverage of Andromeda is slightly better. So with that, I want to say thank you for your attention, and yeah.
Questions?
Thank you. I have questions about the number of variable modifications. How many variable modifications make sense in the end if you analyze this whole lysate? Like if you search for phosphorylation and another modification on the cysteine, and so you have the phosphorylation, your modification, and the carbamidomethylation. That's already 3. Is this still valid, the results, or?
So it's recommended should not use more than 10 variable modifications.
Oh, 10, that's a lot.
Yeah. So, but I mean, if there is really a case that you really have to look for more, I mean, then probably you have to exceed that, but 10 should be still fine.
Okay. So. Thank you.
So thanks for the great introduction. I might jump on that modification train. I always ask myself, is it possible before running the long main search to give us an output telling us about the search space versus the amount of fragment scans we offer to basically judge whether the search makes sense? Is like whether we put too many modifications in, for instance, or not, before actually running the search, because you basically know those things before doing the main search, right? You know how large the search space is in some kind of number, I believe, and you know how many fragment scans we have. Did you ever consider that, or is that an option to go into some files and look that up?
So it's not considered yet. I don't know if it will be. Probably we would need to discuss that.
Yeah.
But it's not
Thanks.
available.
Any more questions? Jan?
I was wondering if it was possible to include also some physical fragmentation into the prediction, because sometimes you're dealing with, for example, cross-linked proteins, and then you submit to cross-link reversal, so high temperature for overnight, or maybe 95 degrees even. And then I was wondering whether there is a probability of breakage of the peptide sequence that can be also taken into account and in the future maybe considered as a physical agent that can break your proteins.
Jürgen?
I mean, you can make the unrestricted search at the moment to find breakage products. I think that would be the way to go at the moment. Is that what you... Okay.
Okay, so if no more questions, then thank you, Petra, for such an amazing talk. And